Dr. Ashley Scott, who's going to talk about a novel manufacturing process for nanofibers and air filtration. Ashley, please take it away.
Thanks, Mike. Thank you all for listening this morning. So I'm going to stay here just briefly, but talk about some of the traditional filter media manufacturing processes. So typically you have your raw materials, which are your natural fibers, your pulps, your synthetic fibers, and they can either be formed into a web via wet lay process, like you're making paper, dry lay process, like some carding lines. And then you have your synthetic resins, which by melting them and putting them with some high velocity air can turn into your spun bonds, your melt blowns, and some of your films. These are the materials that are then taken as a web form and applied into your filters, whether it's a pleated filter, a self-pleat, or even some of the pocket filters used to capture small particles. Next slide. What I'm going to kind of talk about is a novel filter media manufacturing process. And one of the things that Brian mentioned was trade secrets. Well, this is novel to most of the world, but I developed this process back in 2005, and we've been using it ever since. And this is something that we term as called despinning or dielectric ferritic spinning. However, there's a big dielectric ferritic polarization gets maximized and electric conduction is almost eliminated. And that's just an easy way of saying that there's very little current observed. So what mainly happens is that you have a big dielectric difference between the solvent and the polymer, which generates a large force that elongates the fluid beam and produces nanofibers. Now, we've been vertically integrated since we started out in 2005. So we build our machines, we make our solutions. And what's great about the machines that we build and utilize is the fact that we can use common electrospinning solutions, or our special despinning solutions can be used with this type of machine. So when you look at it, it really is a non-evaporative solvent ejection model. And why do I say solvent ejection? Despinning solvent uses very low vapor pressure solvents that doesn't evaporate at any significant rate. We use oils. When you look at the non-evaporated solvent ejection process, what happens is that like I said, we take despinning and we're using from low vapor pressure solvents, really oils. And the oil doesn't really evaporate. So when you look at traditional e-spinning, traditional electrospinning has to come from high volatile solvents. You can use organic solvents, water. And as the polymer is elongated, you get a whipping effect that occurs and you get evaporation. That doesn't happen with despinning. In despinning, we can take our fluid emitter and it can be brought to 1 centimeter of the surface collector and fibers will be dry upon impact. But it's oil. How does that happen? Now, I'm going to go through a schematic of it, but most of the solvent is separated from the polymer within roughly 2 to 5 millimeters from the nozzle tip. And the fiber attenuation will be complete within a single centimeter. Now, if you go to the next slide. I think, next slide, Oh, so here's a schematic of the mechanism. So this is a nozzle that is actually incorporated into an electric field, all right? And upon applying the electrical bias to it, potential to it, what happens is that you get solvent that is ejected horizontally and moves off as nanoparticles. And then you have fibers that are collected and hits the surface. We've modeled this process and these fibers are moving greater than Mach 2, Mach 3, very, very fast. And it's a very, very disruptive process when this occurs. Next slide. So why is this important? So we talk about throughput, we talk about a lot of stuff that traditionally has kept nanofibers from being commercially available. And once again, I would say this is the first time I'm even exposing this really to the world because it was kept as trade secrets. But trade secrets are kind of hard because we had some employees leave us and go try to implement this in other companies. So we can have that discussion about trade secrets and patents later. But what you get is roughly 500 to 1,000 times higher throughput when you're in pure despinning mode. And that's controlled based upon the solvent and the polymer that we're using. Also, it's extremely small electrical power consumption. So some of the systems that we've built, we use thousands and thousands of nozzles, and we operate that system at less than 50 watts, less than a light bulb. You also use inexpensive and non-toxic solvents. This helps keeps our costs down. And our fibers are composed of mostly thermoplastics, but anywhere between 50 to 400 nanometers. And we can control that based upon the solutions that we create. So we can create a gradient if we want to, and we can do different things with our fibers, and the narrow size variance is pretty accurate. Next slide. So this is one of the machines that we have, and this machine, like I said, I built in 2005. And we have many more today that we utilize. But what makes it work, and you see what's big here is composite. What I found out very early on was that you need to make a composite. The nanofibers do not exist on its own because of the various reasons we talked about. There's adhesion, there's making sure that it can be converted downstream. So how we always looked at the market was you will always need traditional medias. Now, we don't make nanofibers. We make composites utilizing nanofibers for various end applications, not only for air filtration, but we also play in paper and packaging. Because of our de-spinning and the throughputs, our price is low enough that we can play in economical industries where no one really can play. So we've been doing this, like I said, since 2005 and very successful at it, but no one would ever know about us because we're under the radar and we do everything on private labeling. This machine right here has the ability to take different traditionally non-woven materials and we combine them together in various ways to make an end composite that will work for whatever that end customer wants. And what's great about it is that we're not limited by any material. We work with a lot of different media manufacturers, and it just depends on what the end material needs to have. So now at the end of the day, you have a composite with gradient nanofibers through it that can capture a range of particles. Next slide. So how are filters rated? One of the great things is that I'm a part of ASHRAE now. I'm a voting member of ASHRAE. But we always look at filters, and filters are rated looking at this MERV chart. And what MERV says is basically you have three ranges. You have E1, which is 0.3 to 1 micron, E2, which is 1 to 3 micron, and E3, which is 3 to 10 and sometimes greater. The higher the MERV number is basically telling you that that filter has the ability to be able to capture more of those particles. A good thing happened in 2015, though. In 2015, ASHRAE finally came to the realization to say, hey, you know what? E1 particles are important. And E1 particles, your small particles, 0.3 to 1, are the particles that can be inhaled, can get into the bloodstream, and can cause damage throughout your body. That's really what's making you sick. And what's even more than that, you have bacteria and viruses on the range of 50 to 75 nanometers can jump onto these small particles. And then you get these small particles and you inhale it. So when you're talking about infectious aerosols and everything else, E1 particles are what we really need to be focused on. The problem is, outside of the spun bonds and the melt blowns, it's very hard for the traditional technologies to capture the E1 small particles without having a huge penalty impact on pressure drop. But what we're looking at is the table, and the table tells you that from MERV 1 to MERV 10, there is no E1 consideration. MERV 1 to MERV 10 is where a lot of your traditional manufacturing equipment exists at. But they're having a hard time getting to the MERV 11s and MERV 13s because they have a hard time capturing these small particles. Next slide. So one of the things that we've done in the past, and this is one example, is that we then said, hey, you know what? I do not want to change traditional technologies. It's needed. It's out there. You have a market that's already utilized. Now, I can talk to that carting line that say, hey, I want you to make one SKU. And you make that one SKU as fast as you can and as economical as you can. And I will take my nanofibers and then I will make that into different grades. So for an example, this is one of the customers that we work with, and this is a standard MERV 8 media. And it's the green line. If you look at it, that's the base material. You can see the E1 is roughly 15, the E2 is 50, and the E3 is 68. We applied two different loadings of nanofibers on this media, and this comes in a composite. So it's just however we decide to make it, and we can greatly increase the E1 capture, which we now termed high E1. So high E1 is one of the trademarks that we actually have out there because we're really, really going after the small particle capture. So this is a high E1 MERV 13 filter. MERV 13 is one of the filter grades that was suggested by ASHRAE to be the most effective at capturing infectious aerosols like COVID. And there are ASHRAE 241 standards that are coming out in 2025 to where the government now, in order to be infectious risk mode compliant, you have to have a mechanical MERV 11A or a MERV 13 in that system. We can use nanofibers to take a MERV 0 to a MERV 13. We can use nanofibers to take a MERV 0 to a MERV 16. You take different composites, though, that are out there in the market to get the most effective efficiency at the most effective pressure drop and the most effective cost. So one of the things, if you look on the right-hand side of the slide, it shows that there is a pressure drop penalty that you're applying with nanofibers because the base media starts off at roughly around 600 CFM, but we're taking the nanofibers down to, with nanofibers, we're taking this composite to roughly 230 CFM, which is still a lot higher CFM than a lot of media on the market today that is not electrostatic. So from a mechanical phenomenon, you talk about mechanical capture, nanofibers are the only way to get the most bang for your buck from efficiency at the lowest pressure drop. And once again, we've been doing this since 2005. So we've been in the market, putting materials together and being able to say, hey, waiting on the market to understand how important E1 fibers, E1 particles are, so that we can have something to capture. Next slide. So in conclusions, these spin fibers have the ability to transform not only, let's say, MERV 8 here, but any kind of low-cost medium into a high E1 producing product, anywhere from that range from MERV 11 to MERV 16. And we do this at a very relatively low cost compared to other products that are on the market. And I am no way saying that nanofibers will take over melt blown or spun bond or traditional cutting lines. I am saying, though, that there needs to be an innovative combination of using nanofibers with the traditional media manufacturing technologies that are out there. You combine them together and you're producing now composites utilizing nanofibers for very high E1 capture, focusing on the small particles, the ones that kill you, cause you health problems, with moderate low pressure drops. And we have machines out there that are doing it. Like I said, we've been doing it since 2005. We've just been doing it under the radar. The other great thing about these products is that it is a mechanical capture. So our products pass Appendix J and ISO 16890 discharge test methods, which once again means that we have a mechanical capture, not a pseudo phenomenon of electrostatic, but it's mechanically capturing these small particles because like, and we can go after capturing your E1 particles to come up with your high E1 materials. So with that, I'd like to thank you for your time and be willing to answer any questions about what we've been doing over the past 20-something years.
All right. Thanks very much, Dr. Scott. And I'm sure we're going to talk more about discharge, Appendix J, and you know, the effects that has on media selections in the rest of the session here.